Monday afternoon. Not Monday, oh dear. Tuesday. I missed my morning coffee. We finished up with limits. So now we move on to the next topic that we study in calculus, and that is the derivative. The derivative came about from what's known as the tangent line problem or the velocity problem. Right? They both boil down to the same thing. So I'll just stick with velocity. So we're all familiar with the average speed. You go 100 miles in 4 hours. What was your average speed? 25 miles per hour. 2 hours, 56 minutes, 46 seconds, and 37 seconds into your trip. What was your speed?
Somewhere around 25 miles per hour.
Doesn't have to be.
Most likely. I can't give you a better answer.
Could be 60 miles per hour. Could be 0 miles. Could be 100 miles per hour. You don't know. Right? You could also take in a 1 hour break where you're not going anywhere, and you have an hour of 0 miles per hour. That is the difference between an average speed and an instantaneous speed. You cannot find your instantaneous speed with that given information. Here's kind of how it boils down. So this is where I'm going to turn to the tangent line problem. All right, so we have some function f of x. Let's call that a. Let's call that point up there b. Line that connects A and B. Do you know what that's called? It's a secant line. What's the slope? So I'm actually going to make a slight adjustment. I'm going to call this, instead of B, I'm going to call it X. And that'll make sense a little bit later while I'm doing that. So what's the slope of that line?
F of x minus f of y over x minus x.
That pink line is a tangent line. What's the slope of that line? You can't assume it's from the scale.
And what's the slope at point A over there?
Right, what's the equation of the line? We don't know that, so you can't determine the slope. Here's how we do it. Take this x, slide it over. Now you have another secant line. What is its slope? Slide it over, right now we're moving this point, and we're constantly finding the slopes of the secant lines. And we do the same thing from the other side. I didn't draw the other side, but it's an analogous argument. Well, what is that process if I'm sliding x to A? It's a limit. Slope of the tangent line is the limit of the slope of a secant line. As your second point x approaches A. From both sides. That is how you would determine your instantaneous velocity as well. You'd have to find average velocities over smaller and smaller and smaller intervals containing that one time of interest that I now forget what time I need because it was an arbitrarily chosen time. I remember 2 hours and 56 minutes. I think 30 seconds? Whatever it was. All right, the idea is the same. And we're going to see what that slope is momentarily. No, it's actually right there. Right, so it's just the limit as x approaches a of f of x minus f of a over x minus a, provided that that limit exists. Replace f with a position function. That would be your instantaneous velocity at A. There is another formula. One that is more useful theoretically. In terms of calculations, this is probably a better option. But for theory and what we're going to discuss next, the formula I'm about to give you is the better option. So instead of using x as my second point, use a plus h, where h represents an incremental change in a. So you could also use delta x. Then what would the formula become? Right, so just replace x with a plus h up here. Limit as x approaches limit as h approaches 0, f of a plus h minus f of a all over h. And so this is also kind of more useful to give a picture of what we're actually doing. Now, we're just letting that incremental change reduce to 0.
So can we do it either way?
Yeah.
Okay.
You get the exact same thing either way.
So it's just a different way of writing it.
Generally speaking, this is more algebraically intensive. So for a lot of the calculations, I'll probably use the first formula. I'll use each one once, and then I'll just pick the easier one.
And it's the exact same value, not more precise or anything. Just the exact
See, it'll give you the exact same value.
Right.
But have to, right? Replace x here with a plus h. That is what you get. So I guess the best comparison I can give would be 1/2 versus 2/4. They both give you the exact same value, just written two different ways.
Right.
Oh, this is how we define the derivative. The derivative is slope of the tangent line. So we would denote derivative in a couple of ways. The first and most common way, I believe this is Newton's way, is the prime notation. So the f prime of a, and it's just the limit as x approaches a of f of x minus f of a all over x minus a. Or the limit as h approaches 0 of f of a plus h minus f of a all over h. Again, depending on the text, you may see delta x used instead of h. It's the same thing, it's just representing an incremental change. And that's all the derivative is. Oh, so the derivative is just the limit. Yes, it is. Which means everything that we're going to spend the next. Oh, God. This is week 4.
I think so, yeah.
I don't know, maybe the next 8 weeks. We spend about the next 8 weeks on derivatives, so it's just more limits. Oh, by the way, when we study integrals, it's also just a limit. So we spend the entire semester doing just one thing, the limit. Oh, but Calc 2 is just more of that. So Calc 2 is also just limits. So is Calc 3. So you waste 3 semesters, a year and a half of your life doing one thing, the limit. Welcome to calculus.
Rather just learn the one thing than a bunch of.
Man, you learn one thing and all the different ways you can use it.
Yeah. Obviously, these are a bunch of separate things.
And you say that, but you actually see what the definition of the integral is.
I didn't say it would be easy.
This is such a hideous limit. You're lucky because I'm one of the few who still teach the formal definitions. A lot of places don't. They don't give the definition, they just give you the fundamental thing of calculus as the definition. And the integral that we study is actually only one type of integral. There's at least 2 that I know of.
At least.
There's also what's known as the Lebesgue integral, which involves measure theory, which is grad topic. Which means you think you get a handle on math. So now we're going to do a bunch of derivatives. Oh! Also going to be plotting, so we're also going to be using mathematics. Which is exciting. I don't think we did, right? With tables, yeah. Now we're going to do it to plot. Wait till we get to Newton's method in coding. I already have a nice project planned for that. So I'll also refer to slope of the tangent line as just simply the slope at the point. Right, so if I go back to here, I purposely drew that to be a slope of 0. So I refer to the slope at A as 0 when I'm referring to a slope of the tangent line. And it kind of gives you an inclination of the incline. And so what would a positive derivative represent? Going up, right? So you kind of like you're going uphill, so increasing. And a negative derivative would represent you're going down. Obviously, the larger the slope, the steeper. What's the equation of the line? Well, that is a line, linear. What's that form known as? Slope intercept. What is the point slope form? Go ahead.
y2 minus y1 over x2 minus x1.
So that's slope. That's the equation of slope.
Y minus y1 equals m distributed to x minus x1.
I use the naught notation, the zero notation, but one's the same thing. Y minus y naught is equal to m times the quantity of x minus x naught. So if we're going at the point x naught, what is y naught if we're given a function f of x? F of x naught, right? Oh, but wait a minute. We're talking about tangent line. For my sanity, I'm going to use A. So that would be the point slope form for a tangent line at A. Would be less ambiguous. Is that x minus a in the numerator is not part of the limit. There's an equation of a tangent line at A. Y equals limit as x approaches A, f of x minus f of A over x minus A, all times the quantity x minus A plus f of A. So if we want this tangent line, the first thing we have to do, find the slope. What's the point? Limit as x approaches 3. F of x. Minus, what is f of 3? All over minus 3. Try substitution. What do you get? 0, 0. Which, if you actually look at the definition, you're always going to get 0 over 0. Right, it's f of a minus f of a over a minus a, which is 0 over 0. So you're always going to have to do algebra. Factor the numerator. How's a factor?
Uh, 2 distributed to x minus 3 x plus 3.
What's that limit? What is it? Slope is 12. $28 minus 36. It's not 8. Negative 8. There's the tangent line. I'm not getting it. Oh, it's supposed to be plus 10x. Plus 10. Oh well. What is this one on the bottom? Uh-oh. Why is, why are you That's isn't good. I just booted you up and you're already making errors. There we go. me use the plot command. All right, so plot command is for functions of the form y equals f of x. Relations of the form y equals f of x. You can plot multiple curves on the same axes. You just put all of the curves together in braces and separate them by commas. So it's what, 2x squared plus 10? And what was the tangent line? 12x minus 8. We need a domain. Minus 5 to 5 for now. See how that works. And that's technically all you need. Problem is, if I go minus 5 to positive 5 on the y-axis, I'm not going to see the curve. I'd like to have more square windows. The plot range command lets me restrict the y-axis. So instead of letting Mathematica choose it, I'm choosing it. No, it's still not showing me anything. Oh, that's wonderful. Oh dear. Useless. So I guess what I could do is do 0 to 40. That'll work. But I could also theoretically do dx. Might do. Set that back to minus 5 to 5. There are other options I can include. So I could include a plot label. This is essentially the title. So we'll convert that into mathematical text. Oh. Now it's doing something weird. That's odd. Split it or whatever. Oh, I know why it was doing that. It was treating that second string as part of the equation and moved it out in front. want labels, we'll just put labels on each curve. So default would be expressions. Nothing really needed for this one. Just showing that as an option. Going to add labels to the axes so that now I can clearly see X and Y. And again, you can let it be whatever you want. The color scheme of Mathematica is not really the best. There's some pretty hideous colors. So I can change the plot style as well. I can tell it to do the exact same thing to both curves, or to do separate things to each curve. So let's say gray, directive, make the tangent line red and dashed. Good. Labels. None. Tangent line. Now, with the desktop version of Mathematica, I can edit this even further. If I double click, you should see if you just click on it once, the outline is orange. Double click on it, it turns gray. That means you're now in editing mode. I don't like where that is. Look out of it. Yeah, it looks a lot better. And then I could copy it into the slides if I had room, which I don't. So. Equation of the tangent line for 2x cubed plus 4x at x equals 4. I think for this one I'll use the other formula, just to show it off. So first thing we need is the slope. Limit. As h approaches 0, f of a plus h minus f of a. What is f of 4? all over H. Four plus H cubed. What's 4 cubed? What's 4 squared? Times 3. 108. 48. Four to the first power times 3. There's 4 plus H cubed expanded out. Also distribute that 4 through the second term. Now we have to distribute that 2 through. $128 plus 16. Oh, that's not. That was so nice. That's 144, isn't it? Minus 144 is 0. 96 plus 4. And I'm also factoring out an H at the same time. What's that limit? That's an easy limit. So, pick your poison, whichever formula you want to use. Because I probably will not be using this formula again. Oh, by the way, there's your calculus. That one step. Everything else was algebra. Calculus is easy. Algebra is hard. And we said f of 4, 144. So 100x. What is 144 minus 400? a slope of 100, that's pretty steep. There's the tangent line. 100x minus, or y equals 100x minus 256. X cubed plus 4x. What do I want the x to go from? Just start off there and see what that gives us. Actually kind of works. Yeah, just leave it like that. Limit as x approaches 4. F of x minus, what's f of 4? What is it?
4.25.
Yes, no decimal though. Give it to me as an improper fraction. Improper fraction.
Improper fraction.
What is it?
5.
Not 5 over 4. Yeah, 17 over 4. We don't ever use mixed numbers anymore in math. So forget you ever learned them. It's always going to be an improper fraction. And typically we don't use decimals. They're not exact. But in this case, 4.25 is exact. That's fine.
Is there a reason, or is it just common practice to not use mixed numbers?
that 4 1/4 or 4 times a quarter?
Good point.
So
So that's
we
fine.
just avoid it altogether.
Right.
And we'll write the 17/4. Over x minus 4. Now I have to simplify. Bummer. What is the LCD?
I don't think we have one here.
We do.
We have one here. X.
I agree, X is in the commons. Not, but it's not in common.
Always take out a 1.
So, first question. We know that x to the minus 1 means. What is it? So it's x plus 1 over x minus 17 over 4. What's the LCD? For x, multiply the numerator and denominator by 4x. And while I'm at it, I'll rewrite it. Put it into its general form for the quadratic. How does the numerator factor? Just like that? Sure? Good. What's that limit? So there's our slope. Kind of a shallow slope. Slope times x minus a plus f of a. Fifteen sixteenths times 4 is what? So there's a few things I have to change. You know, I'm going to keep it as x to the minus 1. Let's keep minus 10 to 10 for now. Let's see what that gives us. So it's actually, we've got minus 5 to 5. So this is where you now need to use discretion. You want to keep that, or do you go, well, clearly since we're looking for the tangent line at 4, I don't care about that negative half. And there's clearly nothing below the x-axis. So I just want to include that positive bit. Doesn't matter. But I don't like where that is. Let's move you down to there. That'd be clearly pointing at the red. And call it a day. Wow, that bulb is garbage. Okay, so that's supposed to be gray. That line's supposed to be gray, not a bright pink. I'm starting to see there's a little bit of pink in that gray as well. Interesting. So what's A? So when you find slope, it should be limit as x approaches what? What is it? An old man. I'm too cheap for hearing needs. F of x. What is f of negative 2? All over what? Write it that way for now. Do we have a common denominator? We do. What is it? This one is easy. It's just x plus 3. We only have one denominator. So we're going to multiply numerator and denominator by x plus 3. Numerator, what are we left with? Negative x, like that. Sure. Hmm? That?
Well, you're done with the numerator, right?
Yep.
Yes, you cancel x plus 3, x plus 2.
Oh, you can't do that. They're attached by addition, not multiplication.
Isn't it -2?
That?
Yeah.
That I think. Or, I'm going to write it. Negative the quantity of x plus 2. Because that serves my purposes better. What is that limit? It's -1. Second line. -1 times x minus -2 plus f of -2. Negative x minus 1, or negative quantity x plus 1. Either one would work. So be careful in Mathematica, just like with calculators. Use your parentheses, use them properly. Okay, well that's just terrible. Oh, 50, okay. That kind of works. Forget your project is due tonight. Things I have it set for tonight. Also, this is week 4, which means on Monday there will be a quiz. First quiz will go up. And that also means exam is also coming up. Right? It's not this coming Monday, it's the following Monday. And that will be in class. Obviously, more details to come. See you Thursday.